The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
What I wanted to share with you is part of rather extensive work that we've done on looking for coming up with the method of maybe not so much predicting as practically checking for potential incompatibilities with admixtures in the modern cementitious systems. We know that the modern mixes are containing typically quite a few components, and once you start putting all of those components together, they don't always seem to work. And sometimes what happens is that you develop undesirable loss of properties, which we call incompatibilities. So what is compatibility? Kind of loosely defining it as interaction of admixture with the cementitious systems that doesn't cause any problems. So you can read what is stated there. Conversely, incompatibility would be a situation where upon addition of particular admixture, the mix does not behave as expected. Then you may get a phone call and say, what do I do? We switch the fly ash, we switch the cement. Everything worked perfectly before and now it doesn't. Everybody in the Zoom, I'm sure, realizes that the reason for those incompatibilities are really coming from the fact that the admixture interact with hydrating cementitious systems. We have a pore solution full of various ions that come from all the components, and chemistry starts playing a role, and if the chemistry is not right, you will have incompatibilities. So the effects will depend, the effect of admixtures will depend on dosage and the type of admixtures they are using, the composition of the mix itself, as well as the composition of the admixture, sequence of addition, water cementitious ratio, temperature, and finally compatibility of admixtures among themselves. If you buy the admixtures from the same supplier, typically those are vetted, if you will. They're supposed to work okay. If you start using air entrainer from one supplier and water reducer from another supplier, that sometimes may lead to the problems. Also, the chemistry of the cementitious material itself and the specific surface area may also play a role. So the issue of incompatibility among the components of concrete mixtures and admixtures, chemical admixtures themselves, is not entirely new, of course, and over the years, the manufacturers of the admixtures developed pretty robust systems that seem to work. But just to give you a brief overview, with respect to early age properties, the incompatibilities that we see are often manifesting themselves as premature stiffening or severe set retardation. In addition, under certain circumstances with the specific combination of admixtures, you may have a problem with entraining and maintaining the air void system. If you start analyzing what might lead to those incompatibilities, you will quickly become aware that you may have cement admixture interactions. That's pretty obvious. You have possibility of admixture interaction that I already briefly mentioned. Or you can have sort of indirect interactions that are combinations of the above. Let's look at some of the components that are really critical when you start talking about incompatibilities in those systems. The tricalcium aluminate plays a big role because that's the compound that starts reacting very quickly right after the water is added to the cements. And we, in fact, make our cements with that in mind. We are controlling the reaction of C3A by integrating clinker with gypsum, right? But if we don't have the balance right, or if we don't have enough sulfates, or we have too much sulfates, we may have a problem. And if the admixture introduces the sulfates to the system, that will upset the balance as well, right? So if you have uncontrolled setting behavior, you will have a flush set. Sulfates also obviously play a role because they control the hydration of C3A. And if you have system that is deficient in sulfates, you will have rapid hydration of C3A, and you will have a flush set. If you have excessive sulfates, you may have a situation when you start germinating precipitation of the gypsum crystals, and you have what we call the false setting behavior. Not only is the amount of sulfate important, but also how soluble the sulfate is very important. So the form of the sulfate that you will find will be also of some consequence. As an example, I am showing the solubilities of 4 different types of sulfates that you may encounter in any cementitious systems. You can obviously have anhydrate, and whether it's a natural anhydrate or synthetic anhydrate will make a big difference. Natural anhydrate is not very soluble. Synthetic anhydrate is comparable in solubility to hemihydrate or to gypsum. Sulfates of potassium and sodium, they are always present in the cements, are very highly soluble, and those sulfates come into the system very rapidly once you introduce the water. Since we were talking about sodium and potassium sulfates, alkalis themselves, alkali metals, they play a role. You may have a situation when you have a higher alkali cement, the rate of hydration of those cements is going to be faster. Since the hydration progresses faster, you will have the appearance of higher rate of stiffening. You will have a potential for a slump loss. So with respect to the amount of admixtures that you would be adding, you will see that dosages are often in direct proportion to the alkali content of the system. If you have a low alkali content system, you will have also lower stability of the air void system. So everything is interrelated, right? In particular, if you have low alkali cement and synthetic air entrainer, you may have problems with the strength loss. We also have fly ashes or other supplementary cementitious materials. My talk today is going to focus on the fly ashes, so I will talk about the role of fly ash. And we know that fly ashes are mostly aluminosilicate glasses with some other minor components, but they, among other things, introduce reactive alumina into the system, which has to be controlled in addition to the need to control C3A. They also introduce sulfates, and those sulfates, if they are soluble, they disturb the sulfate balance. If you have fast F fly ash with a high loss of ignition, you may have a problem with air entrainment. And also, if you have calcium and magnesium that are in the fly ash and coming into the system, you may have a problem with air entrainment because you may have some precipitates forming. These are chemicals that are constituting the air entraining admixture. So, to sum up, with respect to the role of alkalis, if you have a system with high alkali content, you have to typically increase the amount of polycarboxylate type of superplasticizer to maintain the optimal fluidity. If you have a lignin-based water reducers, they reduce the solubility of sulfates, therefore they have disturbing effect on the hydration of tricalcium aluminate. Furthermore, if you have sugar in the lignins, you can have a problem with set retardation and also air entraining difficulties. There are admixtures that can modify the properties of the fresh concrete. Those interactions will affect stiffening or retardation of the setting time. Very often that change in the stiffening is really a function of hydration, of rate of hydration of C3A. There is also a potential problem with overdosing of the admixture. Sometimes either malfunction of the equipment or lack of attention by whoever operates the admixture dispensers may result in accidental overdosing the admixtures. We look at that as well. Key parameters when you start looking at the role of admixtures and potential incompatibilities are really soluble alkali content and sulfate. To give you an example, I took this from one of the published papers. Notice that we have 6 different cements, and 3 of them, C2, C3, and C4, they have very high soluble alkali content with respect to C1 and C2. The overall level of alkalis was not that much different with the exception of those two. But if you look at how the absorptions of superplasticizer or water reducer changed as the function of the chemistry of cement, you can see that C2, C3, and C4, which had a high solubility, they were compatible, versus C1, C6, and C5, they were incompatible. So not only the alkali content, but also solubility is important. So what I am going to do in the rest of my presentation, give you a quick overview, really an example of multi-source interactions and some suggestions how those could be followed and potentially develop into the system that will prevent from them to happen. So we will be looking at potential incompatibility problems in the system that have various cements, various fly ashes, various chemical admixtures. I will be focusing on abnormal behavior related to setting and also to the quality of the air void system. So what we've done, we've collected 20 different fly ashes. We perform analysis of loss and ignition and chemical analysis. We also look at soluble sulfates and alkalis, particle size distribution, magnetic particles morphology, strength activity index, and so forth. 13 of those were class C fly ashes and 7 class F ashes. And you can see the range of chemical compositions and also a range of physical characteristics. We've done a very careful evaluation of those, trying to make sure that if there is some unexpected effect, that we have data to potentially pin down what the result, what the effect may be. So you can see the band of class F ashes and band of class C ashes. Generally, all those C ashes were finer than F ashes. A couple of examples of morphologies of class F ashes. The interesting thing that I want to point out, that very often the deposits on the surface of the class F ash were not sulfates, but they were very often magnetic type of particles. That was in contrast to what we were seeing in class C ashes, where all those deposits that you see were highly soluble, either sodium or potassium sulfates. We also had 4 cements that we used in our investigation. Those are listed here. Notice that 2 of them, cement 3 and cement 4, they had relatively high alkali content, 2 of them were low, and this is the range of sulfates that we need to be concerned with. And for the part of the talk that I will be showing you some examples of the actual data, I am going to focus on selected ashes, 3 out of 20 that we looked at, because otherwise we'll be here for a week and not for 10 minutes. Right? So we have 2 class C ashes and 1 class F ashes. And again, you can see the numbers corresponding to alkali content and sulfate content, and also to the loss and ignition. We used 2 types of water-reducing admixture. One was lignin-based water-reducing admixture, WL, and another one polycarboxylate, WP. And we used 2 types of air entrainers. One was synthetic, and one was rinse-all resin. So this was sort of a flowchart that we followed. We put the materials of interest together. We look at the stiffening parameters, VICAT, mini-slump, semi-adiabatic calorimetry. We look also at the air void stability using the foam drainage test. I won't have time to present that here, but we've done that. And we look at the potential combination. We've done it actually paste, we've done it on mortars, and finally we've done it on concrete. We've done some statistical modeling trying to come up with the variables that seems to be statistically significant with respect to incompatibility, and developed some recommendations. So with respect to mini-slump testing, we developed 2 indices. One of them we called the false set index, and you can see that it was the area of the paddy after 5 minutes over the area at 2 minutes, and if that was greater than 1.3, we deemed that to be illustrating a false set. Then we also have a stiffening index, area at 30 minutes versus area at 5 minutes. If that was less than 0.8, there was a flash set. We also looked at the semi-adiabatic calorimetry. We look at the pastes, in this case it will mix according to 305, and we came up with the set of criteria that one can argue, well, those are your criteria, how do you know that they are going to work? We try to be very reasonable and encompass as many potential variables as possible, so this is based on some statistical evaluation of our data. I already mentioned about the mini snap test, and those are the, if you were, performance criteria, right? We also have performance criteria related to VICAD initial set time, mostly if anything was delayed or accelerated by more than 60 minutes, we consider that to be abnormal behavior. And we also had some criteria related to semi-adiabatic calorimetry. So just a couple of examples. You can see those boxes representing changes, in this case initial set time, with respect to the control mix. So this is a control mix. After adding one of the fly ashes, we reduced the set time, accelerated by right at the border, according to our criteria, 60 minutes. Then if you start looking at the additions of various admixtures, we created a very fast setting system, right? So you can go back to the chemistry of the cement, and you can look at the type of admixture and start drawing some conclusions, which components of the system maybe didn't work out properly. You can supplement those kind of observations of reasoning by looking at the hydration process itself. Again, if you look at this curve represents our system. Doesn't have any admixture, simply cement and fly ash F1 in this case. You can see that when we start adding admixtures, we are changing the chemical response. The rate of hydration is changing, the heat evolving is changing. We are generating the second peak, indication of sulfate imbalance that was created in that particular system. So we observed that kind of behavior in particular with respect to lignosulfonate-based water reducers. They were universally giving us a pretty high likelihood of premature stiffening. We also observed the same kind of relationships with respect to one of those cements in particular, that was cement C2, that was low sulfate cement. We also looked at the amount of fly ash added and how the amount of fly ash will change those balances and perhaps offset the stiffening or setting time. So you can see that it's 20% addition, those four. You have 30% addition, 50% addition, and 70% addition. And surely enough, we've seen the response that indicates that the hydration process and response of the system changes. We had about 18 mixes. I'm not showing all of them here, but 94% of those that were having more than 30% of the fly ash, we've seen significant acceleration happening. Again, that's attributable to the sulfate that was brought and aluminate that was brought and upsetting this sulfate-aluminate balance. 70% of those 18 mixes had set time less than 45 minutes. So obviously that's a problem, right, if you want to hold the concrete and place it and finish it. This is the example how the fly ash content changes the amount of air entraining admixture that was nominally required to attain about 20% of air in the mortar. And basic observation is that with certain air entraining admixture and certain fly ashes, you either see a great increase in the amount of admixture, or in this case, different water reducer and different air entrainer, or actually the same air entrainer used here, didn't essentially change the thing. So it is all over the place. You cannot really easily predict. But the general observation that we came with from this is that at 20% replacement levels by class C fly ash, we will have a false setting behavior in some combinations that otherwise were compatible. Again, this is driven by the combination of the chemistry of cement and the fly ash. If we have lignin type of water reducer and low alkali cement, those in this case C1 and C2, we will have false setting characteristic with fly ash F1, but not with fly ash F2. chemistry of those particular compositions. In certain combinations, changing the flyer source significantly altered the time and hydration characteristics of the base mix. So what do you do? And this is my last slide. What we develop as sort of a flow chart of suggested steps is you probably cannot predict the behavior of those various systems, even if you had all the chemistry for each of those components given, which for admixtures you typically don't. So the best approach that we were able to come up with is to try to do what any engineer will do, try it, right? So if you are suspecting, based on the general trends that I described, if you look at your composition of cement and composition of fly ash, look at the content of sulfates and aluminates and say, that might be potentially incompatible. Try by making a trial mixes and vary one of those variables at the time. So select fly ash with different chemical properties and see if that has caused any changes. Maybe change the type of water reducer, or change the type of air entrainer. That would be with respect to stiffening and slam blows. With respect to air void system, if you have that opportunity, try to select fly ash with different loads of ammunition. That seems to be a common problem. Or maybe change the percentage of replacement, or change the type of air entraining agent. In other words, you have to go and try and check the new combination of materials for incompatibility using some of those tests and suggested performance characteristics that were presented here.